Hello there. How's your day going?
It's good. How about yours?
Doing great. Thank you for asking. Pretty good day, except for the rain ruining my plans. I was really looking forward to having class outside. I was hoping we could maybe find a good place that is accessible to both of us, not too far out of the way, but the rain had to come along and just ruin everything. But other than that,
Yeah, I
not bad
woke
at
up.
all. Pretty good.
Yeah, I
So,
woke up and I turned my or I undid my shutters and on my window there were just raindrops. I was like, oh wow, okay.
yeah, it totally caught me off guard. I don't remember the last time we had a big, heavy rainstorm like this.
Yeah, it's ridiculous.
It's a nice change, though. So, I guess we can start by seeing if you have any questions on the homework, and we can just maybe do a few of them to make sure that our derivative skills are where we want them to be in order to proceed to our next topic. So, do you have
Oh,
any particular questions on the homework?
no, I'm gonna be honest with you. I totally forgot to do it last night. I was working on homework too.
How dare you?
I'm
I'm just
sorry.
kidding. No worries.
Do you think I could do them after this?
Oh yeah, no problem. And actually, you know what? We could just do some of them right now. And well,
Okay.
yeah, I think I'll maybe assign something else for homework on Tuesday, next Tuesday when we have class. But for now, let's just do
Okay.
some of these homework problems on our own. Make sure our derivative skills are where we want them to be. So what if we have this function? Or I guess I want to
Dang
use the function
it.
notation. F of x
Oh man.
is we have e to the 2 times sine of x. And our goal is to find the derivative. We want to find f prime of x. So how do we get
Okay.
there?
Let me just clear up my desk really quickly.
All right. So how do we know what
So
derivative rules we have to use?
I would say we would use the chain rule here because
Exactly right. So what's the kind of the dead giveaway that we have to use the chain rule here?
we have e and sine is in the exponent, but sine is a function of x, or it's taking the sine of x. So there's two functions here.
Exactly. We have a situation where there is a clear outer function and a clear inner function. So e is going to be our outer function, and then 2 times sine of x will be the inner function. So how do we take the derivative using the chain rule, something like this?
Well, we're gonna take the derivative of the outer, then times the inner, and then times the derivative of the inner.
Yep, sounds good. So what is the derivative of the outer?
It's gonna be e2 sine x,
Yep,
e to the two power of 2 sine x,
yep.
and then we have times 2 sine x.
You're close, not times 2 sine x, but times the derivative of the inner function. So the derivative of 2 sine x.
Wait, so e to the power of 2 sine of x is the same thing as the derivative of the outer times the inner?
Not quite. We have almost everything we need. We just need to do the derivative of the inner real quick.
Well, yeah,
So,
but so the chain rule says so it's the derivative of the outer times the inner, and then that times the derivative of the inner. So what we have for f prime of x, e to the power of 2 sine x, that would be considered the derivative of the outer of the inner.
yep, exactly right.
Oh, okay. Okay.
We
And
use
then
our conventional notation. This would be u prime of v. Now all we need to do is multiply by v prime, which is the derivative of the inner function. So what do we get when we take the derivative of 2 sine x?
it'd be 2 cosine x.
Perfect. Very nice. Cool. Not too bad. Let's have you try this one. Let's say we have the function f of x equals 1 over, oh, no, sorry, this is going to be x over 1 minus x squared. How do we take the derivative of this? Show me what that process looks like.
Gonna have to use the quotient rule. So gonna be on the bottom, you always have the same thing, but it's squared.
Mhm.
And then on the top, you have this one. So it's pretty much like it's like the product rule, only you're subtracting. It's exactly the same as the product rule, but you're subtracting, and it goes in the
Exactly.
numerator. The so it's gonna be x, and then the derivative of 1 minus x squared. And then when we use the sum rule, it just becomes negative 2x.
Perfect.
And then in this case, we have minus instead of plus. And then the derivative of x is just going to be 1. So we don't even have to put that there. And then it's just going to be the denominator, the function in the denominator. 1 minus x squared. And here, we might be able to simplify. Yeah, we can. So we'd have to expand this
So
as the
let me stop
negative.
you right there real quick. We want to switch some things around because we're always going to have the derivative of the top times the bottom minus the top times the derivative of the bottom. If we were adding, it wouldn't make that big of a deal because we can add things in any order and get the same answer. But the same isn't true for subtraction. We don't have the same closure under subtraction as we do with addition. So we want to make sure that we're putting things in the right order. So this should appear second, and then this one
Oh,
should appear first. For the product rule, it doesn't matter, but for the quotient rule, it definitely does matter. Here, I'll
yeah,
switch.
my bad.
No problem.
No, that's just me. I messed it up on accident.
Oh, no problem. No problem at all. All right. I'll let you, yeah, go for it.
Okay. Um, so it's the derivative of the numerator first, and then times the denominator.
Yes.
Okay. And then we have minus negative, or no, we could put x first, I
Yep.
guess,
It's going
for
to be minus the
consistency.
top times the derivative of the bottom. Mhm.
Okay. And then
Simplify it a bit, combine like terms.
oh, this might work out really nicely.
Yeah, sometimes it does. Not all the time, but sometimes things work out really nicely. It's kind of unrealistic if you think about it. The book gives us all of these problems that end up working real nicely, but when you're out on the field, if you become a scientist or an engineer or a doctor and you're doing this kind of math, you're not going to have nice numbers to work with. You're going to have
Yeah.
really ugly, messy numbers. So it's
Yeah.
kind of, they're making us have unrealistic expectations of what we'll expect to see in that kind of environment. Looks great. Yeah, perfect. You did that difference of squares factoring. Looks great.
Yeah.
All righty, right. So let's try some more implicit differentiation too. So what we've been doing up until now is explicit differentiation, taking the derivative of something that's in terms of just one variable. So remember the idea of implicit differentiation is that we are taking the derivative implicitly of a function in terms of two different variables. So we can have a mix of variables on either side of the equal sign. So for example, I think I just want to show you a quick example, kind of jog your memory because this might not be the first thing on your mind when you go to bed. You might not be thinking about this all the time like I am, but I guess it's good to refresh. I know I'm crazy. My
I
parents.
remember implicit. It's not that bad. It just has to be you got to do it.
So I had my parents stay with me, or my mom came to stay with me, and my brothers came and had dinner at my house for a bit, and they all wanted to watch a movie, and I had the great idea of saying, hey, how about we just have a math night instead? How about we just get together and do some math? What could be more fun than that? And they looked at me like I'm crazy. Am I crazy, or are they crazy for that?
No, no, just the difference of not opinions, but preferences.
No, I think they're
Yeah.
crazy. I think I'm the only sane one in this family. All right, so let's get into it. So we're going to have the product rule coming into play, and also the chain rule when we take the derivative of our very first term.
Yeah,
So
okay. So,
give this one a try. I need to go grab a water real quick.
okay. I'm gonna get a piece of paper.
All right. Perfect. Looks good. And then
That's
all we
it?
need to do is solve for dy dx.
Oh, okay, yeah. That's what I was about to do. Yeah. Okay.
Here, while you're doing that, I'm going to write another problem up
Okay.
there I'd like for you to try.
Okay, so that's what I got for that one.
Looks good.
Okay.
Nice job. Let's have you try this one now.
And I'm going to use implicit for this one as well, right? Yeah, it looks
How do
like
we
it.
know if we have to?
Um, because we have more, so we're taking the derivative with respect to x. However, we have y here as well.
Exactly.
So we have to just do implicit.
Yep, absolutely right.
Wait, so what does the y in dy over dx mean again? Like what's the wording of it? Because I forgot how you, I know
Well,
like what it means in a problem, but I forgot what it with
that would be
the
the derivative of y with respect to x.
derivative of y with respect. Oh, okay. All right. Thank you.
Yep. And then there's one more problem I'd like for you to do after that. And then we're going to be learning a new topic that builds on this.
Okay, that's what I got for that one.
The denominator should be a little bit different, I think. Nope, never mind, you got it.
Okay.
So go ahead and try the next one for us. Let me move it up first.
Do we
So
have the absolute value of around the the argument of the natural log because you can't have anything negative when you're taking the natural log of it, right?
Right. And that kind of goes
Okay.
without saying. So it isn't even really necessary.
Okay, okay. But it's good to know.
Exactly. Just a reminder that the domain of natural log of x is greater than 0. So real quick, do you remember the shortcut we used to take the derivative of the natural log of any inner function?
Natural log of any inner function.
Yeah, for
Well,
example, or instead
it's
of natural
just,
log of x, what if we had natural log of another function? How do we take the derivative of that really quickly? There's a shortcut. Do you remember the
oh,
shortcut?
I'm doing this incorrectly. Okay. Yeah, no, it's the derivative of the inner over the inner. But I've been
Exactly.
doing this incorrectly. Okay.
U prime over u.
That makes a little more sense. I was I was stuck on the last part.
It's a nice shortcut.
Oh man. Do I have to use chain rule for secant of 2x?
Yes, we do.
Okay. So this is gonna be a process. So first I take the derivative of what's inside the natural log, and then I do the derivative of natural log, right?
Well, remember from that shortcut we just talked about, you don't actually have to put natural log in the derivative as part of your answer. That's just going to be u prime over.
So the derivative of this whole thing, I can just use the shortcut and that's it.
Yep, exactly right.
Oh,
So u
okay.
is secant of 2x. See if you can start by finding the derivative of u.
That's gonna be chain rule. Okay.
Yep.
Um, I think it's secant is tangent. Am I right?
Yep, secant
Um,
of 2x times tangent of 2x. And then the chain rule tells us we just multiply that by 2 because that's the derivative of our inner function.
wait, actually, so the derivative of secant of x is secant x tan x. So that it would just be secant 2x tan 2x. Yeah, okay.
Yep, and then the chain rule tells us we take the derivative of 2x, and that's where this 2 right here comes from.
Yeah, yeah. So that's the derivative of the inner 1 times 2. Yeah, so on top is gonna be 2 secant x, no, secant 2x, tan 2x, and then all over secant 2x. And do you want the answer all under one common denominator?
Yes.
Okay. Is that a dog pouting?
You know, it does kind of sound like that, doesn't it? I don't know what
It
that is.
does. Huh. I thought that was a dog.
It sounds like my dog, and when I don't give him whatever is on whatever I'm eating, I don't give him a piece of it, and then he makes that sound. You gotta see what that
This
is. I'm
is
curious.
all dogs do.
Well, that's actually a really shrill bird tweeting.
Oh, wow.
I think I'll close the window. Give me a second.
Okay.
If you think about it, that's a really smart move because if a cat's hunting for the bird just has to sound like a dog, and then it's pretty much safe, right?
Yeah. As long as the cat doesn't know where the sound's coming
Exactly.
from. Okay, I've got it. Seems like a
All right.
long answer, but okay.
All right, looks good. There's just one thing we can do real quick to simplify it. Do you see an opportunity?
Oh, we can yeah, we'd have to factor out the secant 2x. Okay. So
Yep, but you did the problem correctly. You got the correct answer, so nice work.
yeah, that's a much nicer, cleaner answer.
Oh yeah. So the main reason we even learn implicit differentiation is just because of this one topic called related rates. And that's what we are going to be diving into right now.
Related rates.
Yes.
Okay.
So by this point, we have a pretty good understanding of what rates are and how to use them. One of the most common examples would be the speedometer on your car giving you a reading in miles per hour. We're comparing miles with a unit of time, and that gives us a rate. A rate just compares two quantities. So in this chapter, we're going to explore ways to use calculus to find information that isn't readily available. And we're going to be using implicit differentiation to find solutions. So I like to start with, I want to illustrate this point just with a quick example. So what if we have a spherical balloon and we're pumping air into it at a constant rate? That's my balloon. And the volume increases at a rate of 100 cubic centimeters every second. And then we want to figure out how fast the radius of the balloon is increasing when the diameter is 50 centimeters. And I know that's kind of a lot of information to throw at you. So I'm going to write all of this down as well. So we have air is being pumped into the balloon at a constant rate of 100 cubic centimeters every second. Little 3 right there. No. 3 right there. Cubic centimeters. Perfect. And then what else do we know? We know that we're interested in how fast the radius is increasing when the diameter is 50 centimeters.
The diameter of what exactly? The balloon filled with air, or?
Yep. So I know I'm not good at drawing, but pretend like this is a 3D drawing. So the radius is just going to be the distance from the center to any point on the outer edge.
Yeah, yeah, but that's like when the balloon is filled with air, right?
Exactly.
Or
The balloon is being continuously filled with air, and we're interested in the exact instant when the diameter is 50 centimeters.
so the diameter is 50, so the radius is 25.
So we want to look at the information we have and then understand what formulas we need to use given this information. So we're going to be
Volume,
using
I
the
think.
volume formula. We know that the
Yeah.
volume of a sphere is 4/3 pi r cubed. And if you ever take calculus 3, you'll understand exactly why this is. You learn how to derive this stuff using vector calculus. Pretty
I think
exciting
I
stuff.
remember. I mean, I saw something that sort of explained why it was 4/3, but I don't remember. It was a bunch of diagrams.
I don't want to spoil too much, but you have to do something called the triple integral. You're going to integrate this
Huh.
function rho times sine phi, and you're going to have 3 variables to differentiate and integrate with respect to. So you have d rho, d phi, d theta. And like I said, I don't want to spoil the surprise for you too much, but this is calculus 3 material right here, where this comes from. So I should have erased the volume part of that. I think I'm going to keep the volume right there. We need that. So we want to figure out what this information means in algebra language. So a really common theme in math classes is taking English information and then converting it into algebra notation, algebra language, so that we're able to actually use that information. So we want to convert this into algebra language. Air is being pumped into the balloon at a constant rate. So this is kind of a dead giveaway that it will be a derivative, because a derivative gives us rate of change. They're telling us that air is being pumped into the balloon at this rate. So a rate, that's how we know this right here, this 100 is going to be a derivative. It's going to be the derivative of the volume with respect to time. So we have dv
wow.
dt is
Yeah,
100 cubic centimeters a second. So that is
it's
the
a
rate
rise
of
over
change.
run.
Exactly. This is how fast the volume is changing for a unit of time. In this case, it would be this many cubic centimeters every second.
So the dv and the dt, that's derivative of the volume and derivative of time.
Not derivative of the time. This is derivative of volume with respect.
Oh, is it? Oh, derivative of time with respect to volume.
No, this is derivative of volume with respect to time.
Wouldn't the v be on the bottom in the denominator then?
Not exactly. So it's kind of like when we had dy dx. Remember, dy dx is the derivative of y with respect to x. And then all we're doing is we're just playing switcheroo. We're switching the variables around. So instead of derivative of y, which is on top, we're going to have derivative of volume, which is on top with respect to time. So that's where this notation comes
But I
from.
thought dy of dx over dx meant derivative of x with respect to y. Like you take, you apply all the rules to x, and then y is just another function.
Well, you are correct, but this is the notation we use. So it's a good point. I'm glad you brought that up. So you are right about taking the derivative of something involving x. So we know that we're going to be doing our calculus operations mainly on x. But we're taking the derivative. Do we agree that another name for this thing is called y? Another name for this in the box is y.
Yeah.
So we're taking
That's
the derivative.
function.
We're taking the derivative of this thing. We're taking the derivative of y. So that's why we have the y on top. Y is the thing we're taking the derivative of, and we are comparing it to x. This is effectively just a rate. We are asking ourselves, well, how much is y changing in a unit change in x? So we're taking the derivative of y with respect to x, and that's why the y goes on top. It is kind of confusing at first, but it'll make more sense as we progress through the class.
I see, because our main formula here is the volume as well. So
Exactly.
okay.
They're just telling us that the volume is changing this much every second. And we have the diameter is 50. So notice how our formula has a radius. So we're going to just take half of the diameter. We're going to get r is 25 centimeters. And then we want to take a look at the thing they're asking us and then convert that into algebra as well, algebra language. How fast is the radius increasing? So that's our last crucial piece of information. So I'm curious to see, whoa, I didn't mean to do that. I'm curious to see how, I want you to try it. I'm curious to see how you would approach this next part. So the thing that I'm highlighting in green right now, I want to see if you can convert that into algebra notation. See if you can, convert this into algebra the same way I did with the radius and the derivative of the volume.
Okay.
So what do you think the significance of that would be?
Well, there's a directly proportional relationship between volume and radius.
Mm-hmm. How fast is the radius increasing? So a radius is expanding. The volume is expanding. The radius is expanding as well. So calculus is the science of change. That's the main point of learning calculus. We learn how to analyze change in a lot of different ways. So we have two things that are changing. The volume is changing. The radius is also changing. We have the derivative of the volume with respect to time, but what we don't have is the derivative of radius with respect to time. We want to have the derivative of the radius as well. So what would be the notation for the derivative of the radius with respect to time?
I'm assuming dr over dt.
Excellent. Very good. dRdt, and that's what they want us to find. So let me just ask you real quick, how would you find this, given this volume formula, given that we have a radius, and given that we have this derivative of the volume with respect to time, and also given the fact that I mentioned that this definitely does build on implicit differentiation? How would you find dRdt? How would you approach this?
I think I would use the rate, so we know that we have our constant rate with a really nice number, and that's every second. So we could pick 2 times, like the initial time, and then maybe 10 seconds later, and then divide those two. So you would do, it would be delta radius over delta volume, and then take the derivative of that with respect to time.
You're on the right track. But what we want to do is we want to start with this formula. We want to take the derivative of everything here using implicit differentiation. So we're going to take the
With
derivative of the
respect
left
to radius, or
with
no,
respect to
respect to
time,
volume,
because we
respect to
know
time.
that we want to differentiate everything with respect to time. Volume and radius are both changing per unit time. So we want to make sure we're differentiating with respect to time. So, and then we're going to do the same thing on the right side. So this is just a constant. The derivative of this is going to be 4/3 pi. And then we're going to take the derivative of r cubed. So we get 3r squared times the derivative of r. And then it works out really nicely because we have a lot of information. In fact, we have everything except for the thing we're looking for. We have the derivative of volume with respect to time. We know that is 100. The 3 down here is going to cancel with the 3 up there.
Yeah.
And we have a radius. Radius is 25.
4.
So we're going to plug that in. 25 times 25 is 625.
Yeah.
So this is going to be 4 pi, and then 625 times 4 is 2,500. Here, I think I'll list everything first. So we have 4 pi, radius squared, dr dt. So r is 25. R squared is 625.
Wait, okay, so when we took the derivative of the volume formula, we used implicit differentiation to keep volume as just like a derivative notation as well as rate as well as r
Yep.
in order to just find out what those are equal to, since we know that dv over dt is something.
Exactly. We have a set value for dv dt. We have a set value for r. The only thing we don't have is dr dt, but it's really easy to find that using implicit differentiation.
That's what we want, right? So dr dt shows, it will give you pretty much like if you were to graph how fast the radius would increase, that would give you the function of that graph, dr over
Exactly.
dt.
Exactly. This would be the slope of the curve of the graph that models the radius of this balloon.
Okay. And then 100 centimeters cubed per second is the rate at which the volume is increasing.
Exactly.
And
Every
we just interpret that based off of the words. I mean, not the words, but what they tell us.
Yep, exactly.
Okay.
So now all we need to do is divide both sides by 2,500. So I'm going to start by dividing 100 on both sides.
Yeah.
So we have we're going to have 1 over 25 pi equals our answer. And that's
So
it.
the radius increases by 1 over 25 pi centimeters per second.
Exactly right.
Okay. Okay. Wow, this is interesting.
I'm glad I'm not the only one who thinks that.
I'm gonna write this down because
Please do.
it's just got a little bit of thinking and then you're there.
Exactly. Calculus is a visual art. Pictures help people understand calculus concepts.
Actually, I'm gonna take a screenshot so that we can continue, but then because I want to write down the question and everything too.
Sounds perfect. Oh, and by the way, this is also going to be on my YouTube channel later. You will be able to repeat this as many times as you want if you want to study it later and review.
Okay.
So am I good to erase?
Yeah. Yeah.
Perfect. Let's try another one. We have a ladder that is 10 feet long, rests against a vertical wall. The bottom of the ladder is sliding away at a rate of 1 foot every second. How fast is the top of the wall sliding down when the bottom of the ladder is 6 feet from the wall?
So can we assume in this problem that the ladder started out completely like perpendicular, like flat out against the wall, and then it was sliding?
No, it's going to be resting against the wall. It won't be vertical or horizontal. There will be a bit of a slant to it initially.
Mm-hmm. Okay.
Like I said, calculus is a visual art. I want you to draw a picture of the situation so that we can have a really good understanding of what's going on. Can you do that for me?
Okay. Yeah, I'll definitely try. This isn't going to be the greatest, but okay.
So we want to find dy dt. So this right here,
dy dt.
yes, this right here is y.
Ah, okay, okay.
So
And finding dy over the derivative of that distance would give you the rate at which it's sliding.
yes.
How
So we want
come?
to do something similar to what we did in the last problem. Remember, we had the volume of a sphere to help us out. We used implicit differentiation on that. What formula do we use involving y and also involving the other information we have available?
This one looks like it's going to be
Yes, exactly.
Pythagorean's theorem.
Perfect.
So, but wait, so it's 6 times 6. It's just 8 on the other side, right? Y is 8.
Yes. But because it's changing, because x is changing and y is changing, we
Yeah,
want to
true.
set it up like this. We're going to have x squared plus y squared equals 100. And the reason we're using variables, like I said, instead of the actual values, it's because x and y are both changing every instant. That's
Yeah,
why we
yeah.
put it in this form. So we're going to do implicit differentiation. We're going to get 2x, and then we're taking the derivative of both of these with respect to time. So we're going to have 2x, and then chain rule gets applied here, derivative of x with respect to time. And then same thing occurs on the other side. We're going to have 2y, and then this would be the derivative of y with respect to time, equals 0. So let's look at the problem. Take a look at what information we have. So we already have the 10. Perfect. That part's accounted for. We know that the bottom is sliding away from the wall at a rate of 1 foot every second. So
Wouldn't that mean that dx over dt is 1 foot per second?
exactly.
Because we plugged in x for the bottom part of the triangle, so or for the base.
Yep.
So dx over dt is equal to 1.
Yep.
And then so we have 2x plus 2y over times dy over dt.
Yep. And then they ask us how fast is the top of the ladder sliding down the wall. So we're trying to find derivative of y with respect to time. So
Where it says when the bottom of the ladder is 6 feet away, can't we substitute in 6 for that because we want to know at that exact moment, regardless of the time, we know that the bottom of the ladder is 6 feet away. So we could just so if we want to find out like the rate at that exact moment, wouldn't we have to plug in 6 in the equation?
yeah, exactly right. We plug in 6, and then what else we have is this
The
information right
rate.
here. Yeah, we already have that. dx dt is 1. So
Okay.
we're going to plug things in. So I want to solve for dy dt. So I'm going to go ahead. I'm going to move this to the other side by subtracting it. It's going to become negative.
Can we just move 12?
Where did the 12 come from?
Well, so x is 6, right? At that exact moment that we want to find out dy over dt.
Oh, I see.
And dx over dt is 1. So we would have 12. So could we make like an effort to keep, or actually it wouldn't really matter, would it?
Well, we can get rid of the 2's. We can cancel
Yeah,
out some things we have in common. So we're going to have x times the derivative of x with respect to t equals negative y times the derivative of y with respect to t. So
yeah, okay, this isn't gonna matter anyways when you solve for dy over dt.
exactly, because this right here is just 1.
Yeah,
You have
yeah.
1x.
So it's negative x over y is equal to dy over dx. I mean dy over dt.
Yeah, and that's actually going to be 6. X is 6 in this situation.
Yeah, yeah.
And then we know that what we did, you did the Pythagorean theorem and you got 8 for y, right?
Yeah.
Perfect. Negative 8 and then dy dt. So if we were to just solve for dy dt and simplify it, we get negative 3/4 for our answer.
3/4 because the ladder is sliding negative because the ladder is sliding down.
Exactly right. I was just about to bring that up. It's always a really good idea to check back with our original situation and see if our answer makes sense in the context of the problem. I'm really glad you brought that up because it shows you really understand this really well. Indeed,
Yeah, the
it is
negative
negative
is
because x might be increasing, sure, but y is decreasing, and that's why.
yeah, y is decreasing. Yeah, okay. Because it
Exactly. It's
starts out
always
at
good to
8 at that moment, but it's continue. Okay, that makes sense.
always good
Then
to
in
be in
that
the habit.
case,
Sorry,
what was that?
what did you say?
Nothing. I was just, repeating myself.
No problem. I was just saying that it's always a really good idea to be in the habit of making sure your solution makes sense in the context of a problem. So
Yeah.
kudos to you for that. Let's see if we can do maybe one more.
Yeah. Okay.
So we have a water tank that's in the shape of an inverted cone with a base radius of 2 meters and a height of 4. So I'm going to draw a picture. I'm going to try. So we have the height we have a height of 4, and we have a radius of 2. And we are pumping water into this tank at a rate of 2 cubic meters every minute. So that's how fast water is entering.
Hmm.
2 cubic meters every minute. Find the rate at which the water level is rising when the water is 3 meters deep.
Okay. So I'm assuming we'd want to find the volume of the cone as well, or would that not be necessary?
We do want the volume, and the reason for that is because we have this information right here. Water is being pumped into the tank at a rate of 2 cubic meters every minute. And this is kind of like the balloon problem we did when we were first learning this. We knew that it was volume because air is being pumped into the balloon. This one is really similar. We have water entering the cone, so we know this definitely is going to involve the volume to some capacity. But what
So
formula do we want to use?
it's 1/3 area of the base times height of the prism.
Yep.
So we're gonna have 1/3 times pi r pi 4 pi. That's area of the base, and then the height is 4. So it's gonna be 16/3 pi is the volume.
All right. Here, I want you to write it.
Okay. You want me to just write the volume, or do you want me to like write out how I solved it?
Write out how you solve it.
Okay. I skipped some steps, but it shouldn't be like.
All right. Before we do that, though, we want to use implicit differentiation and take the volume to find the derivative of the volume with respect to time. So we have 1/3 pi r squared h.
Wait, so would the derivative of volume in this case, that would show how fast the volume is increasing?
Yep.
Okay,
And
and then find the rate at which the water is rising. Is that going to be a derivative of like the height of the water rather than the volume?
yep, that would be derivative of the height with respect to time. So we want to take the radius and also put the radius in terms of height. So we know that when the height's
Radius.
4, the radius is 2. And when the height gets smaller, the radius is also going to get
Oh,
smaller.
yeah, that's true.
So
So
we
when the
want to put
water is,
radius in terms of height. So radius is
yeah,
going to be
actually, yeah,
half the
that's
height.
right. We'd have to take the derivative of this. So So 1/3. 1/3 is a constant. We leave that alone.
Hang on. This right here isn't the derivative. Here, we want to move this
Oh, okay.
down a little.
Wait, so what is this? Oh, is that that's the, what is that?
It's just volume.
What's in place of the radius though?
Oh, this one, I just replaced radius with height over 2. And I got that because I looked at the figure and I said, well, I told myself, well, if the height, whenever the height's 4, the radius is 2. So because it's a proportional relationship, the radius is always going to be half the height. So that's why I replaced radius with height over 2.
Okay.
And it just makes it
So
easier
whenever
to
there's a
take.
proportional relationship and you have two values for a certain point, you can assume the same relationship for at any point in the figure.
Well, it's not an assumption. We can tell with absolute certainty that it is because there are no irregularities in the cone shape. I mean, if you're solving a problem like this out in the field, you're going to have idiosyncrasies with this that make the numbers not work really nicely, but we're assuming ideal conditions in this problem. This is going to be absolutely proportional throughout.
Okay, so the direct proportionality is what allows us to do that.
Bingo.
Okay.
Well said. So we want to go ahead and combine our h's together. So we're going to have h cubed, and then we're going to have, this is going to be 3 times 4, because when we square 2, we get 4. We're going to get volume is pi times h cubed over 12. And it's about time to go, but I mean, I don't want to keep you long if you have other stuff to do, but would you be okay with staying and just finishing this?
Yeah. No. I wasn't even, I would rather finish this before we go.
Cool. All right.
Okay.
So we have volume in terms of just height now. So now we want to take the derivative of both sides.
Okay, so we have dv over dc is equal to, this is interesting.
So you have the first part, you took the derivative of volume with respect to time, and then we want to do the same thing to the other side.
So what I'm going to do, I'm going to keep pi over 12 as it is. And then take the derivative of h cubed on its own.
Right.
And since this is implicit, that means we're going to have to do the chain rule. So 3. Now that simplifies. 3h squared times the derivative. Oh, so dh over dt. And this becomes 4. Okay. So, 3 meters deep. When it says 3 meters deep, that's the height of the water, right?
Correct.
So in that case, h would equal 3, yeah. So we could just substitute 3 in there, right?
Yeah.
And then what else? Okay, so I'll do it over here this time now.
All right.
Okay. Oh, wait a minute. We know the derivative of the volume with respect to time. It's 2 meters cubed per minute. Okay. All right. So the water is rising at 8/9 pi meters per minute
Yep,
when the water is
absolutely.
3 meters deep.
Yep, perfect. Nailed
Nice.
it.
Nice.
Very nice. So if you don't have any more questions, you're free to go. Have a wonderful weekend. I'll see you on Tuesday.
Thank you. And I'll talk to you about scheduling the makeups. I should be better about that, but
Oh, no problem. Sounds good. See you soon.
yeah. All
Bye.
right. See you soon. Thank you. Have a good day. Bye-bye.